Hello, this is Adam Czajka again, and I'm going to present my section of this tutorial titled Human Saliency Maps for Designing Human-Aided Iris Recognition Algorithms. That's actually the third part of this tutorial. We learned already what is the iris recognition, and that was a talk by Aidan Bowyer, and also we learned that humans can perform pretty well in this difficult task. So even humans who are not experts in a given task, in this case iris recognition, they can actually perform better than random chance. So if that happens, the question is how we can use this perceptual intelligence, how we can use that to build perhaps better iris recognition algorithms. Iris recognition is here the context for most of the parts actually of this tutorial. But none of the methods presented in this tutorial actually are specifically designed for iris recognition. So hello, this is Adam Czajka again. I'm going to present my section of the tutorial titled Human Saliency Maps for Designing Human-Aided Iris Recognition Algorithms. That's the third part of this tutorial, in which I'm going to say how we can use perceptual intelligence to build perhaps better iris recognition algorithms. So Daniel Moreira actually presented that humans can perform pretty well in this task, which can be surprising because most of the human subjects that we use in the experiment were not experts in iris recognition. But they could use some features, image features that were useful to solve this task correctly. So the question is, can we learn from them? How we can learn from them? And my part of the talk will be devoted to the method that we designed based on information learned from eye tracking recordings. So that will be the core component actually of the presentation, how to measure human saliency using eye tracking and how to translate this knowledge into the effective image feature extractors. So going back to the experimental design, it's basically the same as Daniel presented. So we had pairs of iris images, as you can see here in this slide, and subjects were asked whether these two iris images come from the same eye or from different eyes. You can actually look at them right now and think if these two images present the same iris or different irises. So you can try to find different features in the left and the right image and try to match them. And at some point, you will be certain that this will be the same eye, or maybe if you can't find these features, you will be certain that these are definitely different eyes. So that's the task that we were giving to subjects, human subjects visiting our lab. They were not constrained in terms of time, so they could spend as much time as they wanted. Some of them spent 2-3 seconds, so they were super fast. Some of them spent a couple of minutes. I think that the longest examination was 10 minutes, which is a lot actually for just a pair of images. So some subjects were very, very diligent. Some subjects were pretty accurate and very fast. That was also interesting observation that not all subjects or subjects who spent the shortest amount of time actually were in many cases the most accurate subjects. So the time did not correlate well with the accuracy. The only difference in this task was that we were using eye tracking device to measure where they were looking. So instead of asking to annotate anything, as in the previous experiment, we were just recording this using eye tracking. So that was kind of transparent for subjects. They knew, of course, that there was an eye tracker, but it was for them, it was just effortless. So they did not have to do anything with this, just solve this visual task. Here is an example recording. By the way, going back to this slide, this is the same eye. So if you are solving this task, looking at these two images, this is exactly the same eye, and you can see some features like here, crypt, which corresponds to this feature. Here is another crypt that corresponds to this crypt here. And here is another feature here that corresponds to this feature here. And here's another feature very specific here that corresponds to this feature here. That's basically what the task was. Tell us, what do you think? The same eye or different eyes? Looking at the recordings was also pretty interesting and a lot of fun, actually, because that explains how people are solving this task. So you can see this is a raw recording from one of the subjects, and you can see that this subject was looking at some features on the left image and then tried to match the same feature on the right image, and goes back to the left image and tries to find the same feature on the right image. So it's pretty actually interesting to look how different subjects were solving this this kind of task. New to them, because as I said, people or human subjects that were coming to our lab, they didn't have experience. Most of them didn't have experience in iris recognition. So they actually saw this kind of images for the first time in their life. What we learned pretty quickly was that eye tracking devices, or at least eye tracking device we had, which was pretty actually expensive and accurate, was not accurate enough for this task. Even after doing calibration for each subject before each experiment, we learned that when we asked subjects to look at additional calibration points, so these white points here are the calibration points that we showed before each experiment for each subject, and ask them to look at each point for about 1 second. So as you can see, the gaze, the position actually where they were looking, does not fully aligns with the ground truth points. That was a little bit disturbing at the beginning, because iris recognition and iris features are very small. So we really needed a very good quality, very good accuracy to learn which features actually were used by humans. But that step actually allowed us to build another or extra calibration. And this slide actually shows what we did. So we collected this kind of measurement at the beginning for each subject. An example measurement is actually here showed in blue crosses. So this is where the subject was looking. White crosses are the ground truth points. So the subject was supposed to look at where the white crosses were. But of course, you can see like pretty severe misalignment. But this two sets of points actually allowed us to build a nonlinear mapping or nonlinear warping that translated the blue crosses into yellow circles, which were way closer to the ground truth. So for each subject, we were doing this nonlinear extra calibration that allowed us, hopefully, to be closer to the features that they were really looking at when solving the iris recognition task. Okay, here is an example heat map representing where a given subject was looking when solving this iris recognition task. What you can see right away is that that subject was not looking at the entire iris annulus, but instead of that, he or she was focused on just, I don't know, maybe 15, maybe 20 different features from the iris pattern, which is different from the automatic iris recognition, in which we are using the entire pattern to calculate features and to match these features. By the way, we were using information only from the subjects who were correct. So if someone did a mistake, we just keep that information in processing. So now, how to use these heat maps that represent the human salience in building feature extractor. Now, the first step is to say, where are these features actually? Where are the salient features located in the image? And it's not trivial, because the heat map represents where the subject were fixating actually when just solving this task. But some of these fixation points are not probably associated with features that were used in solving a given task. Some of these fixation points were just like temporary points when transitioning from image to image or from feature to feature. And the literature is not rich in explaining this phenomenon and giving some hints which features we should take into account, especially in the context of iris recognition. Some of the literature that we use suggested 150 milliseconds as the minimum time spent by humans looking at a particular feature to consider that a salient feature. This is associated with some brain processes, and 150 milliseconds should be enough to consciously process this feature as something that is important in pattern recognition tasks. So we assume that's what we should use, but I see a lot of actually room for research here. What kind of features should be considered salient based on eye tracking experiments? So assuming that that's correct, so that we have small iris image patches here, salient, important for humans, how to build feature extractor. Now, one approach is quite obvious. You can train a neural network, a convolutional neural network, that will take these iris image patches and other non-salient patches and will do for us key point detector detection. So like classical sift or surf will be just doing the key point detection, and then the descriptor actually can be also done using deep learning. And that's the approach that we use in another project, and it's working pretty well. And it's useful because it can serve human examiners in the job. So in addition to human examination, we may have another algorithm that will behave like a human and will provide some hints. Oh, look here, look here, look here. I think this is also an important feature. And I think this is also an important feature here. But in this tutorial and in this method, actually, I will describe some different approach. This approach is closer to the dominant classical iris recognition algorithm, in which we are using a set of filters to use this in convolution with the image, and then the convolutional result is just binarized to create something that we call iris code. And this is exactly what John Dugman proposed 30 years ago in his original paper and patent in 1991. So how to build these filters? We were inspired by binary statistical image features proposed by Canale and Rachte 10 years ago, in which they used image patches, not iris image patches, of course, in the original work, but just image patches to find filters using independent component analysis, which can be used to project the image or images onto a subspace spanned by this independent component analysis driven feature dimensions, which means filters in this case. When we run this for iris image patches, here is an example set of 10 filters. Number of filters in this set is the hyperparameter. So original paper suggests from 5 to, I think, 12. So you can choose how many dimensions actually you want in your projection. And it can be different, of course, for different tasks. I think in our case, it was 8 or 10. That was optimal number of filters that we should use in iris recognition. And here's an example set of this filter. So you can see that these filters actually are sensitive to some small blobs. When you compare this to original BC filters, they are mostly, I would say, edge detectors, and closer to Gabor wavelets. So we see some difference when you apply this to a given, at a specific domain. compared to just the regular image recognition task. So this is what we did. And as I said, because these filters are just filters that you can use in any convolutional operation, we replace the Gabor filtering with this BISIF, human-driven BISIF filtering. So we have exactly the same pipeline as the original iris recognition pipeline is. And one difference is actually, the core difference is that instead of Gabor filtering, we have human-driven BISIF filtering inside. And just to remind everyone how that works very quickly, so we have the iris image in this slide. The step A actually takes the iris image. We have the post-mortem sample here because that actually work was done specifically for post-mortem iris recognition. And the first step is to normalize this iris image to compensate for pupil size, which can be different from image to image. So we end up with a rectangular iris image of the same size, independently of the pupil size and independently of the iris image size, which is very useful and very convenient. Then the step B is to take a set of filters. In the original method, it was a set of Gabor filters. In our method, it's a set of human-driven BISIF filters. And after the convolutional operation, part C, step C, is just to take the sign of the convolutional result. So if the convolutional result was positive, we have 1. If it was negative, we have 0. And this is what creates the iris code. Because this iris code has exactly the same structure for each iris, we can use the Hamming distance, or we can use actually the exclusive OR operation to calculate the Hamming distance. It tells us how many bits in this iris code in 2 different iris images are different. In the ideal situation, we should have no difference at all. So the same iris image should have the Hamming distance close to 0. And different iris images should have Hamming distance close to 0.5, because this is like tossing the coin as many times as many bits we have in the iris code. So again, the main difference is actually the between the dominant or classical iris recognition pipeline and this iris recognition pipeline is only actually part B, in which we have a different set of kernels. So one question that probably you have now, how it works. Is it really worth doing, asking many subjects to look at iris images if we have something that works well already? We have Gabor wavelets that work pretty well. So why we should actually spend some time and effort doing that? So here are some results. To measure the quality of this algorithm, I will be using D prime. D prime is a measure that tells us how 2 distributions are different. The two distributions that we're interested in are genuine score distribution and impostor score distribution. Genuine score distribution should be close to 0. Impostor score distribution should be close to 0.5, or should be around 0.5. D prime equal to 0 means that there is no difference between distributions, which means it's a random chance classifier. A rule of thumb is that D prime larger than 3 means that this classifier is actually a good classifier. So when we look at the results, and the first result is obtained for Gabor wavelets. This is based on open source iris recognition software that is pretty known, and you can use it, of course, download and use it. That is based on the original dominant iris recognition pipeline proposed by John Dagman. So we have 6.19, 6.2 approximately. Then what we can do, we can replace this Gabor wavelets with standard BISIF filters. So just take the Canala and Rachtu paper, take their filters, replace this Gabor wavelets with BISIF filters, and try that without any human aided information. the result is a little bit better, but I don't think that the difference is statistically significant. So actually, these two sets of filters, Gabor wavelets and BISIF filters, perform pretty similar in this task. But what happens when we use domain-specific iris image patches? So here we have three different results associated specifically with this task. The first one is when we use random patches. So again, no human subjects, no effort related to collecting any data from humans, just selecting random patches from the iris images. And again, building the BISIF filters using the independent component analysis and looking how it works. And you can see that it works slightly better. I'm not sure if the difference is still statistically significant or not, but it's slightly better, which means that if you repeat the whole pipeline, BISIF pipeline, and you calculate new filters using this method, but the image patches come from the domain, from that domain, it works better. Not surprising at all, right? So if we have a given domain, if we have data from a given domain, and we train a feature extractor on that domain, it performs slightly better than just general purpose feature extractor. That's obvious. Now, what happens if we take patches extracted from human salient features defined by annotations? So what Daniel Moreira was presenting, he was asking humans to annotate some features. So we can use, instead of eye tracking, of course, we can use these annotations and extract this small square iris image patches and just get this information in that way without using an expensive eye tracker. So now we can see that actually this approach is giving us statistically significant better result compared to Gabor filters and standard BISIF filters. That's a good sign. What's the last component? The last component is based, or the last result is based on eye tracker based patches. So, and that is what is giving us the best accuracy here. It means that human salience measured using eye tracker proved to be the most accurate one in this task, which also makes sense because we were not asking people to annotate a certain number of patches of features. They were not constrained by anything, by time or by doing extra tasks. The only thing that they had to do is just to solve the visual recognition task. That's all. And probably the eye tracking, this approach actually collected the most useful information about human charts. And this result, better result than Gabor wavelets and standard BISIF, is definitely statistically significant. The difference is statistically significant. I was pretty happy to see that this method used by other teams proved to be the most accurate among all open source iris recognition methods, which is pretty encouraging. Here is the work by Labate et al. Reporting the lowest equal error rate on a very challenging database of iris images taken from websites and social media, which is not near infrared based database. It's RGB, and probably the resolution was also quite small. So this is why we see quite high equal error rates. But the BISIF method or BISIF based method proposed by us proved to be the most accurate in terms of equal error rate and also in terms of the ROC curve on the right. That's the first work. The second work by Mauro Barni et al. They were also using the same database and reported the best results for this approach for both manual segmentation and also deep learning based segmentation. Again, the equal error rates are quite high, but they are the smallest among all of the methods that they were using in their research. So this is pretty encouraging. And it is also suggesting that this human salience can be really useful in creating feature extractors. If you're interested to use this matter in your work. It's open source, it's in GitHub, so you can download it. The code is in MATLAB and in Python, so you can select the language you like. Don't be stressed and don't be confused by postmortem irises that are there, because that was actually specifically designed for our recent research related to postmortem iris recognition. But this method works also pretty well for live iris images. So a few takeaways from this part of the tutorial. First of all, human salience helps in building accurate feature extractors. That's what we observed here. We observed that using eye tracking device is giving us the most accurate, the most maybe important information of which features were salient to humans. Compared to, for instance, image annotations, which should be confirmed for other domains, not only iris recognition. So that conclusion should be probably taken with some care, but we're happy to see that eye tracking works pretty well. If we decide to use eye tracking, so the third conclusion is that the accuracy is actually crucial. So depending on how big features are in your visual recognition task, you should probably take care of the accuracy and maybe implement extra calibration as we did it for our task. That's one of the things, one of the important maybe hints coming from this research. If you're interested in the whole experiment and how we actually built the feature extractor, how we built this experiment, how many subjects we had, what they were doing. Here is a WACV 2019 paper, which is on archive. I'm also quite happy to answer questions, or I'm sure that all of our team members will be happy to interact with you if you have any questions. And I think now it's time to switch to the second part of Kevin Bowyer's talk about using human salience in iris recognition presentation attack detection, which is a different task, still visual recognition task, but a different task from iris recognition.